All right, just to save some time at the beginning, I've filled in both tables on this helper video. But to get the values, let's see. I'm just going to write a note to this. Values. Okay, so the first column, the F column, you just get by either graphing and tracing or use second graph to get your table. To get any other number, you subtract the number immediately to the left minus the immediately above it number. Let me write that down. So for example, 33 comes from taking the number immediately to the left minus the number above that. Now let's do that. Let's see, make a double negative. You can do that in any of the succeeding columns because you're finding differences. Delta stands for difference. Okay, so how do you tell if a function is quadratic? The second difference this is also called the second difference. When you get to calculus, it will be closely related to the second derivative. Okay, how do you tell the vertex? We can't get it directly, but we can get an interval. So I'm just going to write all this information down, then I'll say it. Hold on. Sorry, delta F, not delta X. Delta F change it. Let me make that prettier. Delta F changes sign from positive if the change is positive, you're going up. That's on the interval between -1 to 0. So from the table, the vertex must be somewhere in the interval between -1 and 0. And we actually know better than this because this is vertex form. -2/3 is in fact between -1 and 0. So there you go. All right. What's the relationship between the rate of change and the leading coefficient? So let's just look at this. I'm going to write this down again because it's up at the top of the page. Okay, this doesn't count. The +4 doesn't count. It doesn't have an x. So the delta f is, and so for a quadratic, let me write it this way. And remember, with the quadratic, a is the coefficient, that the number that we go with for x squared. So the leading coefficient. All right, I filled in this table. Pause and look at it. It's the third difference. So for a polynomial, you can always figure out the differences. Incidentally, I'll do it as soon as possible. However, I'm going to have to do it using using my camera instead of my iPad, because I'll have to show the actual buttons that you push for the calculator. Okay, what's the relationship between, let's see, leading coefficient Let's see, what is this graph? This is, stop it, 2 times x minus 1 times 1x plus 3 times 2x minus 5, so that's 4. The difference is 24. For a cubic, let me put it this way. You can check this with the other tables and the other functions that we've already done. I wonder what's true about the fourth difference and cortex. The 3 times 2 times 1, that's a huge hint. And you'll see the reason for it when you take calculus. Okay, so if the first difference is linear, then the second difference is constant. So the degree is 2, it's a quadratic. Okay, any real roots? No, this doesn't have any real roots. As we know, you can get square roots of negatives when you try and do the quadratic formula. This one has 1 root. And notice that, again, double roots bounce instead of crossing. Okay, what are the 2 roots for this one? X is -1 and X is +2. Maximum number of roots that a degree 2 function can have is 2. So just as a note, we've said it before, but the degree has to be at least as big as the number of roots. Okay, so I know I made this kind of teeny, but 3 real roots. I chose x times x minus 1 times x plus 1. And I got this. I had to zoom in a little. 1 real root, I just added like enough to shove it up a bunch. So I did x times x minus 1 times x plus 1, and then I just added 8. And it makes it do its little wiggle way up here and cross at 8. Oops, because it goes down until it gets to positive. Okay, 2 real roots. We need to have 1 double root. So it can bounce. So I chose x squared times x minus 3. That's going to bounce at 0. And then cross at 3. All right. Yeah, I know. The pagination isn't great on this, but I really wanted to get it out the door as fast as possible. 4 real roots. The degree is greater than or equal to the number of roots. Okay, if we know multiplicities, we count those too. So 2 and 3. And I'm just going to draw 2 mins and 1 max. Okay, here's a min, here's a min, here's a max. That looks like a quartic to me. 3 turning points. 3 turning points means the degree has to be at least 4. Sketching these, I know in advance that there's a root at -1, there's a root at 2, and there's a root at 4. So I'm just going to make that whatever. You can do it yourself. Yeah. If you set each factor equal to 0, you get the roots. Graphing this one, you get okay. It's a double root because of the squared. Okay, and then also at x equals 2, which is from x minus 2 being equal to 0. Groovy. That's fast. Next, how does a double factor? Again, it causes if you're actually watching this, then have a for your information. So you might want to try x plus 1 times x cubed times x minus 1. That actually says crosses at -1, crosses again but flattens out as it does it, and then crosses again at +1. So it's flat as it crosses. The higher the exponent, if it's a even exponent, it'll bounce, and the bigger the exponent, the more flat it is as it bounces. And odd exponent crosses, and the bigger the exponent, the more flat it is when it crosses. Okay, so let's take a look at this. We have x equals -4, x equals -1, and x equals 2, and it's bouncing at -4 and 2. So we have so assuming that the leading coefficient is just 1, we don't have anything else besides x minus -4 squared, and then times x minus -1, and then times x minus 2 double. Okay, so what's the degree? X squared times x to the 1 times x squared is 5. Notice again, odd exponents mean that the ends are going in different directions. One up, one down. How many maxes? This has 2 maxes and 2 mins, so a total of 4 turning points. It is a little tricky to get the number of turning points to be even less than the one less than the degree, but you can do it. I've done it. There's an example in the notes.